Hey, what's up guys? My name is Cherno. Welcome back to my game engine series. So last time we took a look at the renderer, render commands, renderer API, stuff like that, how we can actually kind of like begin and end our rendering and submit geometry and meshes and stuff like that in between. Definitely check out that video if you haven't already. And today we're going to be talking about cameras. Cameras are a pretty big topic, and they're, I think, something that is both like extremely vital for you to know, but also extremely like important that you consider the architecture of cameras and how they work properly. And in order to actually consider how to architect a proper kind of, I guess, camera system in your actual game engine, you need to actually know how rendering works. But not only the rendering side of things, but also kind of the gameplay side of things, because cameras are interesting. They're vital for rendering. You absolutely need to have a good camera system if you want to render anything on your screen. And also, of course, you know that with rendering, you know, you want to make that as optimal as possible, because if you can optimize your rendering, it means you can have more things on the screen and just more time, more kind of actual kind of, I guess, you can have more, I was going to say like a higher price essentially, right? Because we kind of refer to like something being expensive or cheap as to kind of how much time it takes. And what we're kind of paying with is our time, right? Because we have a finite kind of amount of time in which to render a frame. So if you can kind of make your rendering as efficient as possible, you can render more things on the screen. And that's obviously very, very useful. And by more things on the screen, I don't necessarily mean like more objects on the scene. I just mean kind of, you can spend more of your time doing rendering, right? In more kind of in-frame time. And that's really, really important to actually producing high fidelity graphics. Now, there's also the gameplay side of things though, right? Because whilst you need cameras for rendering, a lot of the time, cameras respond to your actual interaction with the game, right? So user input and stuff like that. If I kind of move my character around, chances are it's probably going to move the camera. And so because we kind of have that twofold relationship where it's influenced by both the gameplay, but then also important to be submitted for rendering, the architecture of it is actually a lot more important than you might think. And so because of that, what we're actually going to do today is we're just going to focus on planning. And when deciding to do this video, like I was very tempted to just go into the code and just write a little kind of explain how cameras are going to work and actually come up with like an orthographic camera or something for our kind of 2D scene at the moment. And then just kind of, you know, push that in and actually have that code ready. But I thought it would be a much better idea for me to kind of just spend today just actually drawing like diagrams for you guys, talking about how cameras work and all of that, and how we're going to set them up in Hazel and what the kind of big scale plan is, not just what we're going to do like immediately now to get this thing up and running in its kind of first iteration. The other benefit of this though, apart from just you guys having more of a holistic kind of understanding of camera systems, is what I want you to do is after this video, right, go ahead and try and do it yourself. You have the source code to Hazel on the public GitHub repository, right? Go ahead and just try and take all the information that we've talked about today and write this camera system based on my guidance yourself, right? You might even get some other ideas along the way in which to make this camera system even better than what I'm gonna just kind of plan out here, right? So I really encourage you guys to do that, because if you're just following along with this video, so just going to GitHub and getting the source code and then just like changing, you know, Hazel to your engine name and that's it, you're not really getting anything out of this. So I would really encourage you guys to do that. I want to also thank all the patrons that made this series possible. Patreon.com/thecherno is where you can go to help support this series. You'll get access to source code that I've written already for kind of my version of Hazel, which is like, you know, a full kind of 3D scene and with a PBR renderer and all that kind of fun stuff. And obviously that's got like a full 3D camera system in it and everything, so you can kind of see how that works. And then you'll also get videos like a week early as well. Anyway, jumping back to cameras. So let's just go ahead and go to the drawing board and actually I guess, theorize or talk about how a basic camera system is going to work. And in fact, maybe before we go to the drawing board, I'll just have a go kind of explaining it, and then I'll kind of draw you guys more of the architecture. So cameras, essentially what we want to do is think about what cameras are used for, right? So what I like to do when I think about any kind of concept, right? Because cameras are just a concept. There's no such thing as a camera in OpenGL, right? So you have to think about what a camera actually is, right? So camera is used for, first of all, defining I guess, how we look onto a scene. And I'm going to kind of talk about 3D cameras in this. The same obviously applies to 2D, but I think it's just a bit more like real world and like real cameras in the real world. And it's just might be easier and also more powerful to think about cameras in kind of a 3D context than it would in kind of just a 2D context. Because 2D cameras are usually quite easy to kind of do. And obviously Hazel's going to be a 3D engine, so we need to think about it in that kind of context. But essentially, cameras provide a means for us to view into the world, right? So we have a bunch of objects in our 3D scene, and what we want to do is look at them from a particular viewpoint, right? And not just from a particular viewpoint, but I guess in a certain format as well. So what I mean by that is, like, just like in the real world, you can take a camera and you can put any kind of lens on it, right? Like you could have like a really wide, like 10mm lens or something like that, or you could have like a really zoomed in, like 200mm, right? Obviously, if you're not a photographer or a videographer, you might not understand how these terms work. But hopefully for those of you that are, that's going to kind of make sense, right? You have different focal lengths. And in the same way, that's what we kind of have in our kind of game engine as well, right? Now, we kind of refer to them as field of view rather than actual focal lengths. Although if you do actually create a physical camera system, which you can do, of course, and we might explore that in the future in Hazel, because I'm quite, I would love to kind of go down the photorealistic path in terms of rendering for Hazel. But anyway, if we do that, aside from that, it's usually in field of view, right? So field of view is kind of like how wide or narrow our field of view is, right? So how much we can actually see. You put a camera here, but how wide is the camera, right? How much can we actually see of the scene? Because just having a position of the camera and like an orientation of the camera is all great, but we need to still know how much we can see. And like, if I was to just draw a quick diagram for you, if you imagine that this box over here is like the camera, right? We have a field of view that could be quite wide, which means that if we have, a cube, and this is kind of like a top-down view, or a sphere or something like that, we can see both of them. Or the field of view could be quite narrow, like this. And that would mean that you can see that we kind of clip through the cube and we clip through the sphere. So we could have something like that, right? But this kind of field of view is known as FOV, right? And it's basically usually given in like either degrees or radians. Because we're humans, we like dealing with degrees more. So usually we'd say like a field of view of like 45 degrees or 65 degrees or 90 degrees or something insane like that, right? So usually you probably want to render at about 45, maybe like 45 to 65 is probably an acceptable range. Anything higher than that and you'll start to see quite a lot of distortion around the edges, same as what you would with like a fisheye lens, or even just like even if you get like a fairly wide, like 12mm lens on like a full frame sensor in the real world, and you look at the edges of your frame and you try and take a photo of someone's face, but like they're like over here in your frame, you'll see that they actually end up being quite distorted and it can look quite funny. So that's why we generally want to render kind of in this range. But the idea is that's kind of what a camera is made up of, right? It's not just made up of a position, like, if this is like our scene, this has like an X, Y, Z coordinate, right? And then probably like a rotation as well, which you could give in X, Y, Z. As well, if it was like Euler rotations, or you can use quaternions, which is what we're going to use, and what you should probably use. It's not just that, right? So it's not just a transform, right? It's also other physical kind of camera properties like the field of view, right? There's also an aspect ratio that's usually given, right? And an aspect ratio is just going to basically determine kind of, if the camera should render like this, if it should render like that, how wide is it going to be? Because that's going to be really important as well, so that we can actually fit this properly into our frame buffer, and when we're kind of rendered to our screen or rendering to a texture. So all of these kind of properties define what a camera is, and that's kind of really important to understand. So when I don't understand a concept, or when I'm kind of talking about a new kind of concept, right? So cameras, like what are cameras? I don't know what they are. I don't know how they're going to work in my game engine. The best thing to do is this, right? Kind of break it down into data. What actual data is this, or data, if you're American, what kind of data is a camera? Like, what am I actually doing? When I break these down to actual OpenGL calls, what data do I need to take from my camera and pass into like graphics rendering territory, right? And in this case, as I said, I'm going to need the actual position of the camera somewhere in the world, and the orientation of the camera, and then actual kind of like the properties of the camera, not just kind of the transform, but also the field of view and the aspect ratio. Now, let's break that down even further. What does it mean to have a camera in OpenGL? Right? Like, what does it actually mean? Like, because there's no concept of cameras in OpenGL, how do cameras actually work? Well, what happens is a camera is really, we won't talk about field of view, we won't talk about aspect ratio. Let's talk about the transform of a camera. So it's where the camera is in our 3D world and where it's looking towards, where it's kind of pointing towards, right? What does that actually do and what does that mean? So if I have a cube in my scene and it's at the origin and it's here and I move the camera kind of up and it's going to look at it, right? The thing that's actually moving and the thing that we actually want to do is render the cube at a different position in our screen, right? As I drag the camera up, if I start here and I drag the camera up, right? What's actually happening is the cube is moving from here to here, right? I'm suddenly looking at the cube kind of top down. And again, if I draw you a diagram, we might start with the cube being in the middle of the screen, right? But then as the camera, as the actual camera, which I'll mark with the C, moves upwards, what's actually going to happen is that cube is suddenly going to be more like this in our kind of, view, right? Depending on kind of how you render it, I guess, right? But basically what's going to happen is, and forgive my awful drawing, but we're just going to look at the cube more like this. Yeah, we're going to see the top face of it more, right? Because that camera's moved up. So if you think about what's actually changed on our screen, it's kind of the transform of the cube, right? The cube has gone from us looking at the front face to us kind of looking at the kind of both the front and the top face. So the cube, it looks like the cube is kind of rotated a bit. And again, if we decide that we want to move our camera back, if I just undo like all of this, if we decide that we actually want to move our camera back, right, what actually happens, right? Oh, I don't know how I did all of that in one move. But anyway, what actually happens when we move our camera back? Well, the cube might be, this big because we're looking at it flat on. And then if we kind of just wheel that camera back, right, it's going to suddenly be smaller, right? So what's actually changing on the screen? Well, the scale of the cube seems to be changing. It seems to be getting smaller. So what I'm kind of trying to get into your heads is that cameras don't exist, right? What actually happens is based on the kind of made up transform of our camera, we want to change the transform of our entire scene. And it's important that you think about it as not kind of a per object basis, but really it's the whole scene, right? If I have 3 cubes in my scene and I move the camera back, does one of the cubes get smaller? No, all of the cubes get smaller because I'm going backwards with my camera, right? So cameras affect the whole scene. When you kind of, last episode we learned about begin scene, end scene, right? So when we begin a scene, that's why we push a camera. And that's why I mentioned that in the previous video, because when we begin a scene, we push a camera for that scene. Why? Because when I start rendering a scene, it's all going to be rendered from that one perspective. You walk into a room in real life with your camera, you take a photo of everything, right? Everything in that scene that you take a photo of is going to be taken from that one viewport. Now, obviously, if you talk about more advanced rendering and where we might want to do additional passes or even additional passes with different camera orientations, for example, we might need to render a depth buffer like for a shadow map, or we might need to render like a dynamic cube map reflection or something like that. That doesn't matter, right? We're not talking about those kind of cameras. We're talking about our main scene camera. We have exactly one of those, right? For like every scenario. And it's going to be at a particular orientation. Every single object that we render in our scene is going to be from that actual position in 3D space, right? So basically what I'm saying is that transform of the camera, right? We want to move our objects by that transform. Now, here's another cool question. Like for this, right, we can see that if we move our camera back, we want the object to get smaller, right? I mean, we don't want to actually change the scale of the object. Effectively, that is that's what happens if you're dealing with like a perspective projection, right? Objects that are further away are rendered smaller. But what's actually happening is we're just moving the object further away. So when we move the camera back, we're basically moving the object further away. When we move the camera forward, we're moving the object closer. So it looks like it's kind of inverted, right? What happens if we have our camera and we move the camera left? Well, let's take a look. If we have our camera, let's just say this is our kind of camera view over here, right? If we move this camera left, right? So I'm moving this actual outer kind of rectangle left, the camera's gonna end up here, right? So what's actually happened? This cube is effectively moved right because now the view is like this, right? So moving the camera left moves that right, yeah? What about rotation, right? So what if I kind of tilt the camera forward? Well, this object's going to move that way and it's going to kind of change. But the thing is, the object isn't going to rotate around itself, right? The object is going to rotate around effectively like the origin of the world, but not really, right? This is a bit difficult to think about, and that's why also, if the object was in the origin of the world, then effectively, yeah, like the object would just rotate. But if it's offset by some kind of position, like, so it's got its own kind of position in the world and it's not centered around the origin, effectively what's going to happen is it's going to, like, it might rotate, like it's going to rotate completely differently. It's not just going to rotate about itself. It's going to actually move as well as kind of rotate. But that's a more advanced topic. We really don't need to discuss how that actually works because it will just work if you do your maths properly. And we'll kind of see that in action in the future. So effectively what I'm saying is that everything is kind of inverted, right? So whenever we move our camera left, all of the objects in our scene move right. We take the transform of all of the objects in our scene and we transform them so that they move the opposite way, right? So this kind of data that defines where the camera's transform is a matrix, right? It's a transformation matrix. And specifically, we refer to it as the view matrix. Why? Because it's kind of like our view into the scene. Some people call it like the eye matrix because it's like our eye looking into the scene. But I like calling it the view matrix, which is also a very popular term for it. So this view matrix, what we do, and that's the transform of the actual camera, just by itself, right? If we just take the view matrix, which again is a transform of where the camera is in 3D space, that's what it is. It's just the kind of the transform of the camera in 3D space. So where is it? The translation, right? So where actually is it? What kind of XYZ coordinate in our scene is the camera at? And then the orientation, like the rotation matrix. That's essentially where the camera is actually oriented. That's the location of the camera. However, what we want to do when we actually render from the camera's point of view and we need to transform our objects is we can't just transform them by the camera's matrix, right? By the camera's view matrix. That doesn't make any sense because what we're supposed to do is move the objects not in the same kind of way, right? But in the opposite way. So what we actually need to do is invert the matrix. We need to take that camera's view matrix and just invert it, right? A few ways you could do that. You can actually do that manually just by kind of negating things. So in other words, if I want to move my camera to, let's just say XYZ is equal to 5, so 5, 5, 5, right, is my XYZ for my camera, I can just do negative 5, 5, 5, right? Negative 5, negative 5, negative 5. I can kind of manually invert it, but usually what you would do is you would calculate the TRS, transform rotation scale. Cameras usually don't have scale, so you don't have to worry about that. Translation times rotation, and then you take that matrix and you invert it. And that is actually kind of the transformation you will be applying to all of the objects in your scene. And that's really as simple as it is. So what I've talked about so far has just been the data, right? That is how we get the data. What we do is we take the camera, we position it somewhere in 3D space, we give it an orientation, right? We get that matrix, we construct like a transformation matrix out of those two things, the position and the rotation, right? The orientation, and then we invert it. And that matrix is what we take and we transform all of our objects by. Now, what about the field of view and the aspect ratio? That's like, how is that even stored? The way that's stored is in something called a projection matrix, specifically for a 3D scene and for like field of view and aspect ratio. It's something called a perspective matrix, which basically defines a certain projection loosely, really it's a projection in which objects that are further away have like the perspective effect, right? So they're smaller, right? We have that kind of vanishing point, that kind of idea of just, having like, if I just move down here, of just kind of having this kind of, if you look at like a street and you look at something like this, right? Where, you have like you might have like a bunch of buildings here or whatever. Here's a door, like there's a door. You kind of have that vanishing point where eventually everything kind of just goes into this kind of, and I gotta stop doing that. Everything kind of just goes into this kind of vanishing point in the end, right? And that's kind of what you end up with. So this is kind of a perspective projection. There's also something called an orthographic projection. Usually that's used for 2D rendering. And in that kind of scenario, objects that are further away don't actually get smaller. So in other words, if I'm rendering a cube, right, and it looks like this, and I render a cube that's like far away, kind of behind this cube and a bit off to the right, in a perspective projection, it would look like this. Whereas in an orthographic projection, they would be like the same size. They'd look like this, even though this one's a lot further away. Okay, so we have different kind of projection matrices, and that's stored as a matrix. So this field of view and aspect ratio, kind of all this kind of stuff, right? That's stuff is stored inside a projection matrix, specifically a perspective matrix. And since we're using GLM, we can just construct one of those by just saying GLM, perspective, right? And that will create a perspective matrix for us. And then we can actually, I think there's a function called perspective FOV, and then we can provide the field of view and aspect ratio, and everything will kind of, I think we can even provide a width and height of our actual frame buffer, and it will kind of do the division itself essentially to come up with the aspect ratio that it needs and all of that. And that just returns to us a 4x4 matrix, so a mat4, okay? Now, the camera's transform, as I mentioned, XYZ and XYZ, like transform, being the position and the rotation, that's also stored in a view matrix, which is also a mat4. And then obviously the transform of our object in a 3D scene is also a matrix. So that's TRS, translation, rotation, scale. All of that is stored in a matrix as well, which is the transformation matrix. And then finally, we have the actual vertices of the 3D model. Now I am getting a bit ahead of myself because we haven't covered any of this really, but we will in the future. So this is providing some context. So basically what we end up with is a bunch of matrices. And in order to actually figure out where our object should be on our, like inside our screen, right? We need to essentially multiply all of those matrices together. So what we do is we take the perspective matrix, right? So we have our projection matrix. We multiply that with our view matrix, right? And then we multiply that with our model matrix, which is also known as the world matrix, which is essentially the matrix of our model. So it's like kind of like this, we have this cube, that's the transformation matrix of the cube, right? And then that will also eventually be multiplied by our actual vertex positions, okay? And that is what gives us the full picture of where our actual model needs to be rendered in our screen. And obviously if it lies outside of the screen, it'll just be clipped. It'll be culled. Okay, so that's what we end up with. Now this order is GLM's order, and also the order of multiplication that we see in GLSL shaders, because they're column major. In DirectX, this is the other way around. So you have your vertex position, right? You multiply that with the model matrix, right? You multiply that with the view matrix, and you multiply that with the projection matrix, okay? So it's the other way around because it's row major. And obviously, by the way, like 4x4 matrix multiplication matters. In fact, matrix multiplication order matters, okay? So make sure you do it in the right way. And that's why I keep saying TRS, because we want to multiply translation. We want to do translation times rotation times scale to combine all of our matrices together. Doing them in reverse order gives you a different matrix. Okay, so that's pretty much it. That's all the data that you actually need, right? We've spent a lot of this episode actually talking about data, which I think is good, because that's what it boils down to, right? I want you guys to realize that. We're building a game engine, it's fairly complicated, but at the end of the day, we're just dealing with numbers. These are just matrices, right? They will eventually make their way into the appropriate graphics rendering pipeline areas, and that's what actually allows us to render graphics at a particular place on the screen in this scenario. Okay, so enough about data. I think that makes sense. Hopefully that's enough for you guys to go on and actually make your own camera system that maybe deals with these kind of matrices and all of that. Now let's talk about how the API works. So we have this data, fantastic. My cube has a model matrix, which is a transformation matrix that defines where it's going to be in the world. It's obviously got a bunch of vertices, so I've got my vertex positions. I've got a camera which has a view matrix, right? Great. And the camera also has a projection matrix. Projection matrix defines like the field of view and kind of how it looks into the world. View matrix defines where it is in the world and where it's looking, right? I've got that. So in other words, the part that actually belongs to the camera, just to reiterate, is the projection and the view, okay? Model is actually on the object, and vertex position is actually on like the mesh, right? So projection and view on the camera, right? I've got that. What do I do with that data? So essentially what we need to do at some point is do this whole multiplication that I've just mentioned, right? We have this projection times view times model times vertex position. Projection and view, we can just do that multiplication in the camera. It's, there are a lot of cases in which you will need, for example, just the camera position, right? Not even the rotation, but I just need to know where the position is. That's important for when you're trying to calculate vectors between like a particular pixel and the camera's like view kind of position, for things like lighting calculations. But just for rendering a cube on the screen, which is what we're doing right now, you don't actually need these to be separated. You can just multiply it and that's it. That's kind of your camera matrix, sure. And you'd probably call that something like VP, or, PV. Usually you'd call it VP just because that's kind of the, whoops, I meant to do this. That's kind of the DirectX way of doing things. But the view projection matrix is just projection times view in OpenGL. So you have that and you can kind of just use that. But the model matrix obviously comes from the object. So if I render 3 objects in my scene, that's going to be 3 different model matrices, right? So I can't just kind of bake this in, right? I can do this like once per scene when I move my camera and I've decided that it's going to be in this particular place, once per frame is what I meant to say. I can just bake this I can just do this multiplication, done, right? Every single thing that I render is going to be with this matrix. Why? Because again, I've entered my scene, I've started a new scene, right? The camera's not going to move throughout rendering a scene, right? When you take a photo, no object moves, right? You kind of have the position of it, as in the camera doesn't move while you take a photo, right? You've taken a photo, that's it. It's a snapshot of the scene from that point of view. So this stuff is static, right? It doesn't change. But then the model matrix is going to be the transform of each object. That does change, right? And because that changes and because, you have 3 cubes, you render them at different positions, right? You can't kind of do this multiplication just then and there, right? It kind of needs to be done for each object. And then finally, this vertex position obviously is also kind of done, for each object as well, because obviously objects have unique vertices and they only belong to kind of one mesh. So anyway, what I'm trying to say is that we have this VP matrix, that's fantastic, but then we have to do this model matrix, which comes from the actual object itself. That's why the camera is part of the scene, right? And that's why we submit it when we begin a scene, because we're saying we're beginning a scene with this point of view. Now, when we render the object, there's a few ways to do this kind of transformation. We could actually, technically speaking, do it just in C++, right? So we could say that we've got the VP matrix, right? Let's just go down here, maybe over here, where we've got some more space. So we have the VP matrix. We're going to multiply it with the model matrix, right? Where do we do this? So we could do this in C++ land, but then what we would need to do is actually multiply it, do this kind of multiplication for every single model, right? That's good, and that's probably something you'll have to do unless you use batching or some kind of other instancing in which you probably have like an array of these matrices. There's a few different ways to do it, but essentially you have the opportunity to do this in C++, which means that you kind of do this multiplication and then into your shader, which is where you do the matrix times vertex kind of multiplication, right? So this kind of last step is traditionally done, this kind of last step is always done really in the vertex shader. And that's what we've kind of been doing, but just in a different way, because that's essentially the result of this is what we output into GL position, right? Which is inside our vertex shader, okay? The result of this whole multiplication. So all of that stuff, right, we can do in like this MVP matrix that we end up with. We basically we can take that and we can multiply that by our vertex positions inside the actual vertex shader, and that's our GL position. So you can do that. Or you can do even this multiplication in the shader, and then you kind of just end up with, instead of this, you just do VP times model times vertex, right? And I can't really tell you what the best thing to do is. The obvious advantage of doing it in C++ means that you don't have to do it for every vertex. So a vertex shader runs for every vertex. So if you do it in your vertex shader, it's going to do this multiplication per vertex, which may or may not be worse, right? However, if you do it in C++, it's kind of done per object. That's why we also don't want to do like projection times view times model, because the projection and view stuff, we can just rather do once in C++ for our entire scene and then keep using that data, rather than having to actually kind of do that, per vertex, which is what we would have to do if we were in the vertex shader. So anyway, so between these two, it depends on your setup. A lot of the time you need this model matrix anyway. For example, if you want to translate, normals into like world space or something like that, you'll need the rotation of the model, right? Not the translation really, but the rotation of the model. So this matrix does come in handy, as does this, as does potentially the inverse of this. There's a lot of different things that are important, right? So typically I end up doing something like this in my shader, right? Where I have the view projection, which is my camera. I have the model, which is the transform of my model, right? Of my object. And then I have obviously the vertex data, which comes in the attributes. Okay, so that's kind of what we end up with. So to summarize, what we need to do is when we begin our scene, right? And now we're getting into actual code. When we begin our scene, we want to submit this view projection matrix. And that's why we begin our scene with a camera as a parameter, because we need to begin a scene with a camera. Again, if we had an environment and like a light kind of setup or something like that, like a bunch of lights, we'd also submit those, but we don't right now. But we're going to have a camera. That's what we're talking about now. So we can submit a camera, which basically gives us that view projection matrix. However, when it comes time to render, we might render different objects in our scene with completely different shaders, right? So it's not just a matter of saying, okay, when we begin our scene, let's take our shader and then just submit the, upload this view projection matrix into our shader as a uniform, right? That's what we're going to do. But, and by the way, if you don't understand what uniforms are or anything like that, you should probably look into the shaders video in OpenGL. I actually don't remember if I've done a proper video on uniforms, but if I haven't, it's going to definitely come into the OpenGL series very soon. But anyway, so we need to upload this into our shader. However, we don't actually know like all of the objects in our scene and what they're going to be rendered with, right? Like as in, what I mean by that is, what if we have a sphere that's rendered with one material and therefore uses one kind of, shader number one, and then we have a cube or like a background or something like that that's rendered with a completely different shader. What do we do? Well, what actually needs to happen is that view projection matrix needs to be uploaded into both of those shaders, right? But we don't know that we're going to submit this yet, so we can't actually do that. So what begin scene with the camera should actually do, right, is it's not going to upload any uniforms. It's basically going to do one of two things. It could just save a reference to the camera, right, for later, or like, if you were designing this in a different way, and you had like some kind of uniform buffer to fill, you could actually copy this view projection matrix into like a uniform buffer, essentially, just do like a mem copy or something into a uniform buffer. And then when you actually start rendering with a particular shader, and theoretically your renderer would batch together objects with the same material, by the way, so with the same shader, so that you don't have to kind of keep rebinding shader 1, shader 2, shader 1, shader 2, stuff like that. You just bind shader 1, do all the objects with that, then bind shader 2, render all the objects with that shader. So when you bind the shader for the first time, you have that data inside your renderer. That's the camera that belongs to the current scene. So what you do is you take the view projection matrix from that and you actually upload it into the shader, right, as a uniform. And that's done. And then you render all of the objects. And then you bind in a different shader, you do the upload of the view projection matrix, and then you render all of the objects, right? And that kind of gets uploaded as a uniform, as I mentioned. Okay, and that's kind of what begin scene is supposed to do. The responsibility is, let's grab this camera, let's either save the view projection data from it, or we can actually save a reference to the actual camera. Usually it's better, if you're really being optimal, to just copy the data, because usually this will be submitted into if you've got a multi-threaded engine, it will be submitted into a render submission queue. Taking a reference to the camera is very dangerous, because before the render submission queue might get evaluated, you might have already changed the position of the camera. So it could, because typically multi-thread rendering is one frame behind. So anyway, there's kind of like specifics to all of this that it's like kind of like an asterisk. It might not work if you take a reference. So it's usually generally better to, at that point in time, copy the data that you want, and then kind of put that into basically your render command queue buffer. But anyway, so that's what begin scene does, right? And then when we actually do per object rendering, that's when we take the transformation matrix of that object, which is the model matrix, and upload that into the shader, right? So what I'm trying to kind of reiterate here is that when we begin a scene, we have a whole bunch of actual shader uniforms that we need to set that are part of our renderer. So things like camera, things like the environment, right? Things like the lights, they're not going to change on a per object basis. But then we have a bunch of uniforms, again, another set of uniforms over here that are kind of part of our material. So what is this object we're rendering, right? Is it metal? Is it plastic? How shiny is it? How much should it reflect? Is it wood? What color is it? All of that kind of information, that is part of the material. So we have material uniforms, which are kind of per object or per material, because again, we might render several objects with the same material. And then we have kind of our renderer uniforms, right? Which are basically, you could say, your scene uniforms, or there's a bunch of different ways to call them, right? But they're kind of handled by the renderer, whereas this is handled by the material. So this is kind of jumping ahead into creating a whole material system and doing all the fun stuff that we'll be doing, but hopefully you guys can kind of see the bigger picture than me just saying that cameras do this and that and that's it. Okay, so to summarize, what we need is a function called begin scene that takes in a camera as a parameter, right? It needs to get the view projection from the camera, which is going to be the projection again, which is, you know, this FOV and aspect ratio stuff. And by the way, it's more than FOV and aspect ratio. It's also the minimum kind of cull distance and the maximum cull distance. So we define basically clipping planes that are like near and far clipping planes. So basically, how close can an object be to the camera before it gets culled, and how far away does an object have to be from the camera for it not to get rendered? Because as I said, you know, this kind of creates a frustum, like a view frustum, which is kind of our camera, and then we need to define this far plane, which is this, right? And then we also need to define this kind of near plane. So that's also what we need to do for an actual projection matrix. But we have that. View matrix is basically the inverse of the camera's transform. We need to take that data, we need to put it into our renderer when we start a new scene, right? And then when something gets submitted, which right now in Hazel, as soon as it gets submitted, it gets rendered, we actually need to see what shader we're submitting that mesh or that vertex array with, right? When we bind the shader for that, we also need to upload, in this case, both the view projection and the actual model. So that's kind of the architecture of this whole thing. And end scene really does nothing, right? Still kind of does nothing. You could have it clear if you were copying data, you could have it clear the data. I don't know, I wouldn't probably do that. In any case, you could just have you could just keep track of whether you're inside a scene or not. So you could say like m, you know, scene or whatever equals false or null or whatever, and then that way, if you try and render something that you haven't called begin scene, or you call begin scene and you call begin scene again without end scene, you could like assert and make sure that it's like a little protection thing that you do, but end scene will have stuff in the future, obviously, but not right now. Okay, so that's kind of the idea of this whole camera system. Hopefully that makes sense to you. Hopefully this is enough information for you guys to try and figure this out on your own before I implement it in the next video. But yeah, this is like this is the whole basis for scenes and renderers and stuff like that. So it's all very exciting, and you can see that it leads to really, really cool system in the future. Anyway, I hope you guys enjoyed this video. If you did, you can hit that like button. You can also help support the series by going to patreon.com/thecherno. You'll get access to source code earlier and videos a week earlier, as I said in the future. If you're watching this live on YouTube right now publicly, and you're not a patron, you can just see the next episode immediately right now if you just go ahead and help support the series. Okay, so as I said, next time we're gonna actually dive into the C++ code and the shader code and everything like that and actually make this happen. We're gonna design an orthographic camera, not a perspective camera, because currently we're kind of dealing with just 2D rendering. And we could do a perspective camera, not sure, but we will obviously eventually do that anyway when we have a 3D scene. And from there, I'll probably want to maybe, I don't know, we'll branch off into several things. We might just talk about them when we actually get there, and I'll try and kind of do something that you guys want to see. But effectively, we could continue on with 2D rendering and actually maybe make the camera controllable and also make it so that we could render multiple objects on the screen, and then we could even make a 2D game or something like that. Or we can just kind of do the base level work for that and then just move on straight to 3D, depending on what you guys want. I mean, I'm probably more keen to do 3D, to be honest, because I love that stuff. But we'll probably make Hazel more usable for actual 2D games more quickly if we did this first. So it's kind of up to you guys to decide. Anyway, in the next episode, we'll implement this stuff. Make sure you have a go on your own before you actually look at the next episode. I will see you guys later. Goodbye.